Let me begin and share my presentation. And let me know once you can see it. Just a second. Let me know if it's visible.
Yes.
Yeah,
Okay.
I can see it.
Yeah. So thank you everyone for being here. This is part 4 of a 5-part series. This time we'll be talking about Kubernetes workloads, a bit of a deep dive into all the objects and workloads available in Kubernetes. Not in particular all of them, but the core components, the main ones. So before we begin, just a little bit about myself. My name is Ahmed Harb. I have over a decade in experience in Linux system administration, mainly cloud, DevSecOps, automation, containers, and microservices. I'm the founder and owner of Codeathon, and I'm a senior cloud and DevOps consultant with ObjectSharp, they're Microsoft Vault partners. And I've incorporated my LinkedIn profile. If anyone would like to reach out outside for any questions or anything, feel free. I'm glad to connect with anyone in the community that's looking for any advice.
Technology questions through the Microsoft Teams, but any personal help, yeah.
Exactly. Yes. Exactly. Yes.
Thank you.
So just a quick recap on the previous part. So we discussed the Kubernetes API, that the core Kubernetes control plane is pretty much an API server. It exposes an HTTP API, HTTPS to be specific. The users and different parts of your cluster will always, as well as external components, will always communicate to one another through that API server. Additionally, we covered objects, and to make it easier to eliminate the fails or restructure things in Kubernetes. One more thing to mention about the API: it does support multiple API versions at a time, as well as API groups. This is something essential to keep in mind. And Kubernetes objects were covered as well in the last part. It's pretty much that a Kubernetes object can be defined as a record of intent. It describes your cluster's desired state. And your cluster, Kubernetes itself, is designed in a way to make sure that the object is always, the state that you are describing is always being matched with the current running status. So the objects are made of 2 parts. There is the spec and there's the status. The spec is a desired state you provide, and the status is what Kubernetes tries to always match with that spec. And 100% of the time it is going to match for sure. So objects are described also in the API in JSON format, but to make it simple, the kubectl client tool usually just takes a YAML template from you, and it will transform it when you try to deploy. Additionally, I mentioned a few ways to set up a small test cluster, either Minikube or Kind, if you want to set up a test cluster. And we covered a bit on Kubernetes namespaces, which can be defined as the fact that Kubernetes supports multiple virtual clusters in the same physical cluster. So these virtual clusters are called namespaces. They are intended mainly for to be used by large teams who are sharing the same cluster. And the last piece we covered were labels and selectors, which are the main grouping functionality in Kubernetes. So labels are like key value pairs. They are attached to objects either at creation time or later on. And they're intended to specify some identifying attributes like the environment on these objects, like the environment they belong to, whether it's QA, UAT, dev, whatever you want to name it. You might have multiple environments, dev 01, dev 02, and so on. The app name, for example, if you're running multiple applications in there, the version that you're running, and so on, the component they are part of. There are a lot of, it's very flexible, and you can reflect whatever you have in your organization to with these labels. Again, I keep repeating this, but just to keep in mind that Kubernetes is complex. We're doing our best to explain it in the easiest, simplest way possible, but there is no really a very simple explanation for it. You have to take what I'm sharing and read further and build on that to have full understanding of it, and definitely practice and use test clusters as much as you want. And I also have these helpful resources always repeated in here. The first one is the holy grail of Kubernetes, which is the Kubernetes documentation. You will not find any better source for learning than that. The second one is a link from Microsoft. It does simplify Kubernetes. It has from beginner to advanced features about it and things that relate to AKS, the managed Kubernetes service from Azure. The third one is a 6-minute long video by Brendan Burns explaining how Kubernetes works at a high level. He's one of the founders of Kubernetes, and he's currently a corporate VP at Microsoft, handling AKS, Azure Kubernetes Service, and multiple parts of Azure as well. And the third one is by Kelsey Hightower. He's a really prominent figure in the Kubernetes community, and he has a GitHub repo called Kubernetes the Hard Way, where he pretty much gives you step by step of how to build Kubernetes clusters from scratch. It's not the best way. I definitely advise with managed Kubernetes services for actual usage, but this will give you full understanding of how Kubernetes runs for sure if you go through all these steps. So to begin with the Kubernetes workloads, the first one to be covered here is the Kubernetes pod. So pods are the smallest deployable unit of computing in Kubernetes. Kubernetes adds that new level of abstraction for container management, which is the pod. So Kubernetes sees the pod, but the pod has that container in it, one or more, right? So to define pods, they're a single atomic unit with co-located and co-scheduled one or more containers. Okay. So pod comes from the naming of a pod of whales or a pea pod. Everyone has their definition for it or how they think it's where the origin of the word is. I think it's more of the pod of whales because everything is following that aquatic theme in the world of containers. It's a group of one or more containers. They share like storage, network resources, and the pod has the specification of how to run these containers. Okay. So they share everything except for CPU and RAM. So each container is going to run its own C group. C groups are short for control groups. There are a Linux kernel feature that limits and accounts and isolates the resources for every container from a CPU, memory, and disk I/O respective, and even the network in and out for a collection of processes. And in the case of containers, it's going to be for every container on its own. So they will share these, they will not share, you have the ability to give them dedicated memory and RAM for each one of them, but at the same time, they will continue to share the file system, the host name, the IP addresses, the port space of wherever they are deployed. So usually you don't create pods directly, but you can, but usually don't do that because they're considered like orphan pods. You will have to maintain them and make sure they're up. You're not really leveraging the power of Kubernetes to handle that. Instead, you would create them with a controller resource. We'll get to these in details, but something like a deployment or a job. So the pods, that will be the controller loop tracking your pods and making sure they're always available. If it dies, it will create another one for you rather than you having to keep an eye on that. Additionally, they are designed to be ephemeral and disposable entities. So keep that in mind. You do not build pods to live there like VMs. I've seen this happen so much. A lot of dev teams will choose to give their pods a very high memory and CPU for no reason, or they will build even their container in that way. That is a very bad practice. They are not VMs. They should not be treated as VMs. But I will add also, you should leverage from multi-threading and running multiple pods at the same time, horizontally scale, not vertically. Because again, what's the point then of running any container or running on Kubernetes? So keep that in mind. So you should design them in a way that you don't care if a pod goes away. You care about your service that is running, and the pods are just simply backend. So the pod is not really a process. It's actually an environment of running containers. The containers are running a process. The pod is how you describe this environment. You can give them shared storage with volumes. You can give them, you decide the memory and RAM they get, and then Kubernetes decides where it will put that pod based on the best place for that allocation, right? You can also configure how you want it to go, right? You can also configure what happens if the processes within it fail, it will restart them. So think of it as an environment for containers, not as the container itself. A few important things to discuss about pods. The first thing is the pod lifecycle. Okay, so after you send a creation request for a pod, and that creation request is accepted by Kubernetes API. So you gave it a correct template. The Kubernetes API said, yeah, that looks good. The pod will go into the first state is the pending state. Okay, the pending means that it's waiting to be scheduled by Kubernetes. If you remember our presentations previously, in Kubernetes, there's a kube scheduler in the control plane. That's the one that finds a node for every pod that is in the pending state. It doesn't. So if it gets stuck in that pending state, that means you don't have resources where it can be scheduled. So if your nodes are full, your pod will just live there. Even if it's missing 10 millicores that it needs, if you have set that up in this request, it will not be scheduled. So keep that in mind, plan it ahead, and be sure of having enough resources on your nodes to schedule all your pod replicas that you want to schedule, as well as account for any auto scaling you might configure. Okay. You might also, consider, optimizing the requests of CPU and memory that your pods would ask for. Once a node is found by the scheduler and the pod is attached to that node, the pod will transition to the creating state after the scheduler finds that home for it. Okay, creating means that a few things will be happening. The images will be pulled if they're not available, or depending on your policy, you can set it to always pull the container image and the startup of these containers. It could stay stuck in that creating state in case it cannot pull the image, but then eventually you will see an error that says error pull image or something like that if it's not able to pull the image, for example, or if something breaks in the startup, you will see an error as well. And if your pod fails many times, the next step would be either it goes to a failed state and it's stuck in that error because it cannot start up, or it will go to the running state. Okay, it goes to the running state, and it might quickly transition to that crash loop back if it's failing continuously. So the running state is once it's bound to the node, all the containers are starting, they go to the running state. But within less than a second, like it's rare for you to even witness the running state. You will see that the pod will either be either it stays in the running state, or it could go into a crash loop back off state. So once that happens, if the pod is failing too many times, it will start to be restarted by Kubernetes because it's self-healing. It will look that, okay, this is failing, I'm going to try to start it again. It keeps doing that. If it happens too many times, the API server will start backing off pretty much. Okay, so it will, for example, it will start it once every 10 seconds. If it keeps failing, it will increase that timer to 20 seconds, then 40 seconds, and so on. Up, I think, to 5 minutes is the maximum, and then it just gives up on it and considers it to be failed. Okay, so in case your pod is actually terminating, it's not a running process continuously, it just reaches an exit zero pretty much as a process, and it does what it needs to do, then it will go to a succeeded stage, and that's it, it's completed. Additionally, on the other hand, if it continues to fail and it reaches that end of that crash loop back off, it will just be a failed state, and that's it. Depending on your restart policy, you can configure, because again, the pod is an environment, right? So you can configure a restart policy in there. If you configure it to always restart, so you have three options. You can set it to always, or on failure, or never. The default value is always, but if you set it to never restart, it will never restart. You will just have that pod in a failed state. If you set it to always restart, it will always restart. Even if it succeeds or it fails, it will restart. So typically you would want to, if you know that your pod is going to succeed and at the state that is completed, it doesn't need to run again, you will put a policy of on failure. That's when I want my pod to restart, for example. right? So this applies to every container in the pod. Even if you might have, remember, the pod can be multiple containers. You might have one container in there failing and leading to a failure being detected in that pod. The whole pod will be restarted, not one of them. So keep that in mind. Okay. And there are rare cases where the pod could go to an unknown state. That's when if it's on a node that has failed and the kubelet is no longer sending in the status of the pods there to the API server. So you will see an unknown state. Typically, again, that's another reason why you would not run a pod directly, because if it's an unknown state, if it's under a deployment, that controller loop will create another one to replace the unknown one, and it will remove that unknown one from its replica. And if it's under a service, it will be removed from that service as a backend. Another important thing that I've seen developers ignore a lot, and they are very essential in pods and for your application logic and how it should be working, is the pod probes. So there are 3 probes in pods that you can add. This is how you can configure the checking for your application, whether it's alive or not. So there are 3 of them. There's a startup probe, there's a readiness probe, and a liveness probe. A startup probe pretty much is used by the kubelet to know when a container application has started. If you know, like if such a probe is configured, it's liveness and readiness. So this is the first one that is running. If you have it running, this is if you have added it to the template, this is the first thing that's gonna run. Okay, and the readiness and the liveness probe will be disabled till the startup probe is done, to make sure that they don't interfere with that. So it can be used to have a liveness check. It's pretty much like a liveness check, but on a slow starting container. So if you know your application takes time to start, and this could happen for multiple reasons. Maybe it depends on another backend that might be slow to respond or something. There might be many situations where this could happen. You would avoid that it would get killed, right, by kubelet before it gets the chance to start. So let's say your application takes for some reason takes 5 minutes to start. Kubelet will probably kill it a few times before it gets to that. It doesn't expect it to take 5 minutes to start, because the liveness and the readiness probes will start to check, and it'll say it's not ready, I'm gonna kill this, and restart it, and you will end up with a restart loop when that's not the intention. So you can add that startup probe that takes, around let's say 5 minutes. After the probe is done, it will make sure, okay, it's alive now. Then it will start up the readiness and the liveness probes, and your container is ready. So you avoid that kubelet is restarting it for any time. So again, in short, it's very useful for pods that have containers that take a very long time to come into service and start up. The fate of your pod, if it's restarted, is decided by that restart policy we mentioned earlier. The second type of probe is the readiness probe. It's used by all these probes are used by kubelet. Okay, kubelet is that component on the nodes that looks at the pods and communicates any status and any values. Every state of it is communicated back to the API server. So the kubelet will use these readiness probes to know when a container is ready to start accepting traffic. Okay, so when a pod is considered ready, it's only when all the containers inside it are ready. So if you have 2 or 3 containers, your pod is not considered ready till all of them are ready. So keep that in mind. Okay. One use of this is the fact that it will signal to the control which pods are used as backends of services. So eventually you will expose your pods or your deployments as a service. You will add that abstraction layer. We will get to that part, but that's how you would do it. What decides, and this service load balances to the pods as the backend. Right? So you want to tell your service, this one is ready, please add it to the backend. That's pretty much what a readiness probe does. If you ignore adding a readiness probe, you will have the default one, which as far as I remember, I'm not 100% sure, but I think it's like around 5 seconds and it'll start checking, and it just does like a HTTP ping kind of thing on an endpoint, like randomly. It's gonna definitely give fake results or false positives in many cases. And if you care about this, this even 5 seconds of impact on your clients, or 10 seconds in your application is up, you will see traffic being sent there when it shouldn't be, and it will be dropping, and it will impact the quality of the service you're giving to your clients. So Kubernetes gives you this ability to control it, right? And if a pod fails, it's at the same time it's removed from the services backend. So it's very essential to keep that. Okay, this is something to keep in mind. As you see, the default is after, if you have an initial delay, it will be to fail unless whatever condition you put in that probe has succeeded, or else it will be a default success. So the readiness probe will directly say this is ready, right? Within a few seconds, as soon as the pod is up, it will directly say this is ready. The container has started. This is ready. Let's send traffic to it. That's not the case with a lot of applications, right? You might still be connecting a DB or whatever is going on in your application. So be careful of that. It's very important. So the main use case, and it's very useful to make sure that containers are, they might sometimes be temporarily unable to serve that traffic. So you would want to add that readiness probe to make sure that they are actually ready to do that. And don't just add a readiness probe that does, like check 200 on an endpoint that is just static. That's not really, I see that's usually, either they don't have a probe or they will add something like that. That is really not helpful at all. You should add an actual check endpoint, like a health check endpoint, that makes sure, the connection at DB is in place, that this application is responding properly, or whatever logic you want to build that actually makes sense, that this application is ready to serve. And the last type of probe is the liveness probe. Okay, so this is how you tell Kubelet, as we mentioned, Kubelet restarts the pods, right? But depending on your restart policy, obviously. So if you have a restart policy of never, you don't care about this. But if you have an always or on failure, the always also maybe will always enforce that. But on failure is, you need to decide what's the failure, right? Okay, how do I control what means that my container has failed, right? So this pretty much tells the kubelet, how or when to restart that container. This is what kubelet uses to decide that. Okay, so for example, the liveness probe could catch a deadlock. This happens, right? Everything might be perfect in your application, but it might, it's a process at the end. It might be stuck in a deadlock, and this application is running, but it's stuck in that deadlock, and it cannot do any progress. The only solution is to restart it. This happens, right? Did you try to turn it off and back on? This is a common thing. It might happen eventually in anything, right? So the only solution is to do that. You're not gonna go and do that in every pod. You're not gonna do that, right? That's really difficult. And how do you even detect that? You have to enter the pod, because for you it looks, oh, it's ready, it's running, right? And even if you send to a service, it will load balance. It might be sending to that sometimes, maybe to others. It's going to be very difficult to keep an eye on that, especially we're talking in hundreds or thousands of pods, right? So what would happen is you let it up to Kubernetes to do that, leverage the self-healing power of Kubernetes. So, but you configure the logic of how that happens, right? Again, if it's not provided, the default is success, but that's bad as well. If your application gets stuck, it's stuck, right? So what you want to do is build that logic, right? To detect that log or what happens in that application. If it's not really responding anymore, well, please restart it, right, on my behalf. So you're giving it the permission to do that on your behalf whenever a certain logic is happening. So again, it's very useful to detect and fix any pods with containers that have went to a broken state that really requires a restart. There's no other solution to do that. Okay, so that's something to keep in mind of. It's very important whenever you work on an actual live application. Please make sure to add pod probes. This is very important and should be considered from the beginning. This is something to plan ahead, not add later on. Another important feature that is in the pods, as you run your application containers, you can also run something called an init container. Okay, an init container, a pod can have multiple containers. They're running these apps inside it. but you can also have one or more init containers. These run before your app containers have started. Okay. If the init container fails, Kubernetes would restart your pod until the init container succeeds. Okay, so make sure you add an init container that will actually exit with a init containers do not support any probes. Keep that in mind, because they always run to completion. Okay, so they don't support any, they don't have a life cycle like the pod, or they don't have support for any probes, because they are made or designed in a way to always run to success. They have to. Okay, so make sure you build init containers in that way if you ever need them. So keep that in mind. The main use case of that is to add in it any utilities or setup scripts that might not be present in your app image. Maybe you have certain setups to happen ahead of time that are not part of your image. Maybe you want to build one image that you will use in multiple containers. In one case, I'm going to add certain directories and certain initial setup that I want to do. Maybe I want to, make some secrets available to the init container, but not to the actual app image, and save them somewhere or initialize my application somehow. And then so on, the application will continue without access to that secret, right? But the init container have done what is needed for the application to start up. Things like that. Think of it in that way. It's very, very helpful to add init containers, but they must complete before the next one starts or before the actual pod starts. This will actually plug into the lifecycle first, something you will see called init. You will see an init state in that pod lifecycle where it runs first the init containers, makes sure they're successful, and then it goes on and runs the others, your actual application containers. Okay, so it does two main things I see as a very helpful use case of init containers. The first thing is to block or delay your application till certain preconditions are met, right? So you build according to your logic. I have certain conditions, certain initialization need to happen. I would use that till to block, and it would indirectly block my actual app container to start till I've passed all these preconditions. Okay. Second thing, it will help to limit any attack surface on your app container images. A good example of that is actually Istio, maybe the old way, but in the new way there are other options. But Istio init container, there's always an init container. Whenever you add a sidecar to a certain Istio is a famous service mesh. We'll get to that, but it will add that init container as well. The init container actually runs at a more privileged state than your other containers, because it needs to manipulate the IP tables in some way, and add all these proxy sidecar, need to add some IP table rules and all of that. So that init container has a bit of an elevated access. You don't want to give that to your sidecar proxy nor to your actual app container, right? That's a bit of an attack surface that you're exposing. So what would happen is that init container will run for 2 seconds, do what it needs to do, and then it goes away. It's not available anymore. There's nothing with any elevated access. Okay, so that's a use case that is for example, very common to happen. So one more thing that's important when you build your pods is to always keep in mind these requests and limits, right? So this is how you tell Kubernetes, how you want to limit your CPU and memory that are being given, and they're given per container, not per pod. Okay, so you can set different limits for different container. If your pod has 2 different containers, one of them needs more than the other in terms of CPU and memory, you can do that. Keep in mind the limit can never be lower than the request, because it's not technically a min and max, but to a certain extent it is. Like, it's the minimum and maximum. So think of it in that way. The requests are the minimum that is needed, and the limit is the maximum. But it doesn't mean that it will always use that minimum. That's why I'm saying it's not really a min and max, right? Because in the requests, it just tells the kube scheduler that this needs to be deployed on a node where these minimum requests of memory and CPU are available. So it will keep looking for that. So keep in mind, don't put very high levels and thinking that it will not always use that, because technically the scheduling of it will depend on that. So it will only schedule it in a resource or a node that can provide that resource. Okay, So so the requests are what the container is guaranteed to get pretty much, because the scheduling will only happen in a place in a node that has that minimum available. But whether it uses it or not, that is different, right? So it might be using way less than that. Keep that in mind. So it's good to do some load testing, be sure of what your container needs before you schedule or you plan these limits and these requests and limits. Okay, so the limits make sure that your container does not go above a certain value. So they're pretty much like a max level. However, when it comes to CPU, they're not really an absolute hard limit. What would happen is when it goes to that limit, it gets restricted. If it's in memory, it will be killed with an out of memory, an OOM exception. It will be killed by Kubernetes. It will have to be rescheduled. So memory is very critical, because memory is not elastic like CPU, right? CPU is elastic. CPU is pretty much the time. It's a compressible resource, right? It's the time that you're taking out of the CPU pretty much, right? So if you are hitting that limit in CPU, you will get throttled. So you will be getting less time than you want, right? But in memory, no. In memory is not compressible. This is what I want. If it is exceeded, you will be killed and sent somewhere else, right? You can use this hand in hand with resource quotas and namespaces and limit ranges as well. There's another object you can create. So on namespaces, you can create quotas for every virtual cluster in there, that this namespace will have only a combination of 5 cores for the CPUs of all the pods within it, and 10 GB of memory for all the pods in it, for example. You might create 20 of them, you might create 5 of them, it's up to you, you know, but keep that in mind. You can use it hand in hand if you want to also keep a bit of tight constraints on your namespaces as well, or these tiny virtual clusters within your big cluster in terms of resources. This is a sample template. You know, it's pretty much a way of how you're gonna tell your container how much memory it has. So it's pretty much would create an Nginx container that has starts with a 400 millicore of CPU. So this is 0.4 core pretty much. Okay, one CPU is one core on one vCPU on cloud providers. Like it would be equivalent to one vCPU on a VM on Azure, for example. Okay, and 600 meg of memory, but memory is, you know, it's the same standard as in meg or gig. You can put GI for gig if you want, but yeah, so it's pretty much it. It's telling it, okay, find a node where it has at least this much, and my you know, container expects that it needs, this is the minimum it would need. It might use less than this. At certain times, it might use more, but make sure it doesn't use more than this value. If it exceeds the memory, it will be killed. If it exceeds the CPU, it will be throttled, and you will see degradation in your performance for sure. So Kubernetes controllers, these are the fun part of Kubernetes. They're very important. So the first one is the replica sets. So it's pretty much a method of managing multiple replicas of your pods and their life cycle under one controller loop. Okay, so you pretty much, it relates to how the pod will be scheduled, how it will be scaled, how it will be deleted. It plays a simple role. To summarize it, it ensures that you have a desired number of pods are running. Let's say I have a certain application that I want to run it on 3 pods at a time. I can create a replica set. I will suggest later that the replica sets are not really used directly, mainly, you know, through a deployment. But if you want to do that, you can use a replica set if you don't care about versioning of your application and you know, rolling out new versions and stuff like that. It doesn't really own the pods; it just selects them. These pods have to be identical. Keep that in mind. You give it an identical template and it will do that. So it makes sure that you have a given number of identical pods that are up at any time. You can also actually have it adopt existing pods by using certain labels, or you remove the label from the pod and these pods will be quarantined. So actually, if you suspect that one of the pods is having an issues, you can do that and it will be out of that replica set and technically out of the service as well. Okay, so when you scale it down, though, keep in mind it will randomly delete one of the pods. It will not do it, you know, like out based on a certain standard. So usually you typically would not use them directly. You would use them through a deployment. But one example use case is a static website. So if you have a static website, I don't know, like a redirect page that you will always show that will not change much. You don't care about, you know, deploying multiple versions or so on. That's where you would use a replica set and just deploy, let's see, say 2 pods of that, and that's what you care about, right? I have a link to a sample template that you can look at if you want for while you're playing around with your test cluster. The second type of controllers is DaemonSets. DaemonSets are pretty much a way of making sure that you have a pod running on every physical node. Okay, you can run on specific nodes by using node labels and selectors. Again, labels and selectors are the grouping method in Kubernetes. This is how the API works. Okay, you can use it for nodes, for pods, for services, for so many things, pretty much everything. So you can perform a rolling update on this. This is a feature of deployments where you can update the version of your pods or roll back to a previous version. And anytime a node is added, a pod will be added to them as well. So from the name, a daemon set, like daemons are in Linux terms, it's something that you're running as a backend service all the time, right? So it's really ideal. The ideal use case of daemon sets is any cluster-wide services, something like logging and monitoring. Other services, there's like QRed is very famous as a service that detects if the actual node has been patched in a way that it needs a restart. So that QRed agent will be running that it will actually restart that node, it will evict the pods from it and then move them to a different node and then restart that node. And once it's back up, Kubernetes by default does not balance things out, but it will be the next choice for any new deployments because it's pretty much empty as a node at that time. Right, so services like that are the typical use case of a daemon set. I have a sample template as well for you to look at. Other two types of controls are jobs and cron jobs. So jobs are pretty much configured with, they create one or more pods and ensure that specific number of them will successfully terminate. Okay, so it's from the definition of the word. Right? So as the pods successfully complete, the job will track these completions. Okay, so you can define also if you want parallel pods to run and the expected completions that you want. Okay, so the job will complete when the specified number of completions have been reached. Let's say I want to run a certain thing 5 times. Okay, because a job will actually deploy a pod to run the container that you have defined in that template. Okay, so you say you want to run a pod 5 times and to completion 5 times. Okay, so you're gonna go ahead and do something like that. Like you will create a job that we'll run this pod with this template for 5 times completions. So it will run it the first time, complete it. The second time fails, it will restart and then it completes and so on. It will track these 5 completions that I have decided. There are different patterns of how you would do this. There's one-shot, parallelism, or work queue. The difference between them is the one-shot is when you set one pod at a time and one completion. Okay, so it's a one-shot. You just run it one time, and I want it to complete one time. Right. In a parallelism situation, the pods will be more or equal to 1, and the completions are also more or equal to 1. However, the pods will never be more than a completion. Okay, so you would make sure that I want to run. If you put more than one pod, let's say 2 pods, and I want 4 completions, so that will run 2 pods, complete them, and then run another 2 pods and complete them. So the queue is when your pods are more than 1, but the completion is not set. So the pods will run until they all finish. Okay, and no new one will be created until after they're done. So you can build like a queue of jobs that are running in there. Cron jobs add on top of jobs the ability to execute these with a cron-like schedule. Okay, so it's very useful to create periodic and recurring tasks, something like backups or sending emails, or let's say you are writing things to a certain file share, you want to pick them up from there and send them somewhere else every 15 minutes. You can have a cron job, deploys one pod, runs for 1 minute, takes the things in there, send them somewhere, right? Or send an email with the list of the files, whatever you want. Take a backup of things. There are so many tasks that can be done in a schedule. Like the main advantage is that you are not running this pod continuously, right? And checking continuously because there's no need to do that, because maybe my actual files are created by my application every 10 minutes. So I will check every 15 minutes, take it and send it somewhere, right? Instead, and this will help me save on the memory and the CPU of my cluster instead of running these tasks continuously and assigning them this request and limit all the time, right? So it's the cron job is pretty much an extension of the job controller. So you add you have inside the cron job you have a job, and that job has a pod template pretty much. Okay, and the times are usually based on the time zone of the kube controller manager. The kube controller manager is the part of the control plane that handles these loops, right? And it's mostly in UTC, but it depends. Anyways, I have two templates here, one for a job, one for a cron job. Feel free to use these as a starting for your testing. Now deployments are the most common and use case for deploying any application in Kubernetes. So they're a way to manage pods using ReplicaSets. Okay, so the deployment controller will actually will change the state to the desired state at the controlled rate. Okay, based at what you want. So what would happen is the deployment will actually create a replica set of pods. Okay, that replica set will be handling a certain number of pods. So you give a deployment a certain template that has replicas, the number of replicas, and in it the template of the pods that you want, right? So identical pods again. The main features of it is that it gives you that image version update functionality, right? So you can roll out a new version, you can roll back to the previous version using this deployment. Okay, it keeps track of these. At the same time, if let's say I update my image, I have a CI/CD pipeline where I update my new image. I send my new image to whatever container registry I'm using, and then I deploy a new template referencing the new tag of that image. I have a versioning tag in that image, and then I update that template of the deployment inside the cluster real time. That cluster, that deployment, if it detects anything in that pod template, let's say some things are immutable, you cannot change, like the selector, for example, you cannot change that and make it select different pods. You have to create a new deployment. But things that relate to that pod itself, I give it a new configuration. I change the image of that container inside it. I add a container in there. It will automatically trigger a rollout. So what will happen is the deployment will create another replica set in a controlled fashion, another replica set. That replica set will start deploying one pod. It depends on your strategy, right? Usually you can either do a recreate or a rolling update. A recreate will actually kill everything one shot and then create the new ones. I wouldn't advise that, obviously. A rolling update is better. It's a controlled fashion way. You can put some percentages, or you can leave it by the default, which is 1/4 at a time. So if you say have 4 pods, it will kill one pod and create it under the new replica set with the new template, and so on. Once that is ready, it will keep track of that. Once it's ready, it will do the second one, and so on. Once everything is done, it will delete the old replica set, and all the traffic will go to the new one. You can leverage horizontal pod scaling, and I would highly advise that to do automatic scaling. So you can attach that horizontal pod scaling to your deployment with a certain limit of CPU. Let's say if the CPU exceeds 70%, please scale it up to 5. So you can set, for example, I want between 4 pods and 6 pods, for example. So, and it will do that on automatically. So without really doing any timeouts in your application or any issues, it will just tell that deployment, please add one more because your CPU has reached on average more than 70%. It will add another pod and add it to that deployment, and it will be traced automatically. The best example of it is any dynamic application. And by dynamic, I mean any application that needs to have version updates often and it needs to be scaled often. That's what you would do. Use a deployment. There's a sample template here that you can look at. It would be very helpful. Now off to Kubernetes load balancing. There is one more controller, which is stateful sets. I did not cover it. You can also look into that in the Kubernetes documentation. It's mostly for any application that keeps state within it. Some people have ventured into deploying DBs on Kubernetes. I'm still not a big fan of that. But certain UDBs, CrushDB and others are actually built to run that way. You would use something like a stateful set, but you can look it up in the documentation and delve into details if you have any use case like that. It's not really common to have a stateful set on Kubernetes. Kubernetes load balancing. So the main component is the services. That's how you abstract. It's an abstract way to expose a running application on a set of pods. It gets abstracted and exposed as a network service. Okay, because your pods are mortal, they're ephemeral. they are born and they die and they go away, right? And they are not resurrected. They're not, you know, they don't have any miracle there. So if you use a deployment to run your application, it might destroy and create your pods dynamically. If they fail, you scale it up, you scale it down, they change, right? Things happen, their IP will change, right? Each pod gets an IP, but the problem will be like, okay, these pods are between quotes, let's call them backends, right? They provide the functionality for your application, right? You have another piece on your application that has a front end. There are another set of pods that are running that front end in your cluster, right? So how would that front end keep track of the backend? If it's gonna track these IPs, that's nearly impossible. It's very difficult, right? So the balancing of the load will happen automatically by Kubernetes. Every pod has its IP and it's balanced across it as long as they're part of that same deployment, right? But you want to abstract them because you want to have just one endpoint that is static and you're pointing to it to have your application run without any issues. What happens in the backend, I don't care because I know these pods come and go away, right? I need something to abstract it away and allows me to have that decoupling between my front end and back end without having to keep track of what's happening or changes that are happening. That's what you use as services, right? The service that you create will target certain pods by a selector. A selector is labels. It will match. Okay, I have a front end service. It will look for app equal to front end. These are my pods for my front end. You will usually use a combination of them, right? You'll have also an environment because you might have a QA front end and UAT front end that are different. So you'll use a combination that makes that service in the Kube API server, you know, in that object in your Kube API, match the correct ones, right? And they get an internal DNS name. That internal DNS name will always follow the format of service name, .namespace, .svc, .cluster, .local. So you can depend on that. You can depend that this is how they will be reachable. And you typically, even within the cluster, because all of the pods in there, the front-end pods that need to talk to the back-end, they just need to reference the service by name, by the way, .namespace even, or just by name if they are in the same namespace, and they will automatically resolve to that endpoint, to the full endpoint, and they will do properly, even if the backend has scaling happening. So there are different types of services. The first one is cluster IP, which is the default. There is node port, load balancer, and external name. Cluster IP pretty much exposes the service on a cluster internal IP. It's only internal to the cluster. So if you choose to use that, that service will only be within your cluster. Okay, so that's the default. If I want to expose a backend only within my, and this is good from a security perspective as well, right? If my microservice does not need to be exposed outside, I just keep it within my cluster. I create it as a cluster IP. I don't need more than that, right? Node port will expose that service on every node IP on a static port. It will choose an upper limit port, like in 32,000 plus or so, and it will just expose it on there. It will actually also have a cluster IP on the backend, but it happens automatically for you, and the node port service will route to that automatically. So you will be able to actually reach it at node IP, column port number. Your nodes usually have a private IP within your network, right? So you would be able to reach it there. So that's very helpful to use sometimes. Again, I really haven't used it much. I usually go with a cluster IP and then a service mesh with only one load balancer outside. The other service is the load balancer. That's the way you can expose your service outside your cluster by using a cloud provider's load balancer. Okay, it will also create a node port and a cluster IP on the backend, but all of that is automatic and abstracted away for you. It will typically give you just a public IP on a load balancer. It will even automatically create that load balancer for you. In AKS, it will automatically, you either have that out of the box, or if you want an internal one, it will create for you an internal load balancer. And obviously, I would advise to go with an internal one, then you can expose it with a more advanced tool like APIM or API management or app gateway or something that is, with better functionality and more security, and you can put a WAF in front of it. So it will automatically give you that cloud provider load balancer to expose it outside your cluster. So if something comes to that endpoint, it will automatically go to your internal service for you. You don't have to do anything. Everything happens natively. And the external name is pretty much a way to abstract or simplify any external services by giving them a service name within your cluster. So you would, let's say you have a Cosmos DB. outside your cluster in Azure that you are using, but you want to give it a simple name, let's say Cosmos DB QA01 inside your cluster. So you create an external name service that is pretty much the URL to that Cosmos DB outside, mapped to a simple service name within your cluster, and then you can hit it that way. Your services can just easily access that. A higher level load balancing is done by Ingress. So that will manage external access to your services, and typically it's HTTP or HTTPS. It gives you load balancing, SSL termination, and name-based virtual hosting. It would fulfill any. You need to create an Ingress controller first. An Ingress controller is pretty much a load balancer service that's running a certain proxy server, like Nginx. Ingress controller is one of the most common ones. I would typically leverage a more advanced solution like Istio, which has a service mesh solution with a lot of security capabilities, plus the Ingress control as well. So your Ingress rules typically consist of a host and a list of path, like URI path you want or subdomains, and you map them to a backend. Okay, so you will say that, for example, svc1 myapp.example.com / QA will go to this service / whatever will go to the other, and your subdomains, you can have multiples of them as well, right? Based on what you have configured, and you can configure a TLS termination to happen at that Ingress controller. It's very helpful. There is a template there for you for reference. The last parts are about the Kubernetes config management. I will run through them quickly, and then we'll get to Q&A. We have maybe a few minutes left. So again, make sure you decouple your configuration from your. We covered this from the first presentation. Through container. When you build a proper container application, you do not bake anything into it. Make sure your configuration is outside it. And Kubernetes gives you all the tools you need to do that. ConfigMaps is where you store any non-confidential data. Any application properties, anything that is not secrets will be done there. It doesn't provide any secrecy or any encryption. You use ConfigMaps to that. It allows you to actually run the same container on your machine and in the Kubernetes cluster, because if you build it in a way that the config map, you just provided a config map and it decides how it functions. If you're on your machine, you give it a config map that is locally working, it will work. If you give it one in an AKS cluster, it will work. If you give it one in a cluster you have built your own, you can also work in OpenShift, it will also work, whatever you use, right? So it allows you to decouple your application code, which is the container, from the actual configuration, right? So you can use them as either environment variables, or you can mount them as read-only files and read them from there. And you can even write code in your pod that will pick up the config maps from the API continuously, right? So it's really, really helpful to utilize something like that. So let's say you're testing a DB, you can give it just a config map with a DB host. Don't put the secrets there, okay? Secrets are different. So you give it just a host and a config map. In your system, it will be a local host, and you can run it with that config map. And on the cloud, it will be whatever URL for that host, right? Or will be that external name service that you have created. Secrets, they are functionally very identical to config maps, but there's a big difference. The difference is they are for sensitive information. They are encrypted at rest in etcd. They allow you to save any sensitive information like auth tokens, SSH keys, passwords, so on. Whatever is a credential, please put it in a secret. You store them as base64 encoded, but this is a common mistake. Base64 is not encryption. It is not. It can just be taken and decrypted. It's really easy. But they are stored, at rest in an encrypted manner, and they're treated as a secret in the cluster by the API. So you also make sure, not anyone has access to secrets. By default, the common RBAC in Kubernetes do not have access to secrets. Okay, so they are safer and more flexible than putting them in a definition of the pod, passing them as an environment variable on the config map or in the image. Because if someone gets your image, they get your secret pretty much. Keep that in mind. So make sure you don't do that. Okay, so there are three types, which are generic, Docker, and Docker registry, and TLS. Generic are any of them that you want to, like any literal values that you want to give. As a certificate, the TLS are just a TLS certificate-based secret. Docker registry are the credentials that you authenticate with your registry. It says Docker registry, but it could be any type of registry. Usually they follow the same standard in terms of credentials. The last two pieces about storage. So storage is abstracted using persistent volumes, and the way you use persistent volumes is by persistent volume claims. So it gives you an API to abstract that storage. They represent that storage in the backend. They are cluster-wide resources, and they're linked to a certain storage provider like Azure Files or Azure Disks. They are usually provisioned by the administrator. Keep that in mind, because you need to have that link with these in the backend. It involves some secrets to connect to it. They are independent from the lifecycle of the pod, and they cannot be attached to a pod directly. They're done through a PVC claim. There's a template in here you can go through. And PVC claims is the last one, which is a namespace request for that storage that you have created by the user. So it's not done by the admin. The user will use a PVC to claim that PV created by the admin. So the same how pods consume nodes by asking for a certain CPU and memory, the claim is the same way towards the PVC. So the PVC claim will consume that PV by claiming a certain size or a certain access mode. You know, if I want to mount it as a read-write once or read-only many or read-write many, depends on what is supported by that, right? Azure Files supports everything. It's really, I really advise to use Azure Files. It's really great. And it satisfies these sets of requirements by mapping them to the local storage. So it also ensures that your claim is portable by multiple to other backends. Let's say the pod goes away, PVC is there, the other one can pick it up and go on. So there is another Azure File PVC template that you can use here, and you know it would be hopefully helpful. You should do your best to practice all these types. The templates are a good reference, but there is much more you can find on the Kubernetes documentation. So if any questions are there, I would be glad to answer them. I know this took a bit long, but I wanted to cover as many as possible of the objects.
Wonderful, Ahmed, as always. Great work.
Thank you.
Questions, please. If you have any questions, you can unmute and ask. No questions. So it's looks like Ahmed, you're crystal clear then.
Hopefully.
Hey, Partha, yeah, go ahead. Ask questions. Yeah.
No, I don't have any questions. I'm just saying that there's a lot of information there, and many of us are still beginners in Kubernetes. So it's not surprising that there are not many questions.
Yeah. Understood. And as you all know, the recording will be posted in next 2 to 3 days in the YouTube. And once you have an account of the Testoper community teams, you would also be able to get access to the presentation, because we don't want to put the presentation public. So once you have an account, you should be able to get access to all the presentations, not only this session, all other sessions that we are doing. Those who do not have the account, feel free to send your email addresses. We will add you into the Teams account. Well, last chance.
Kader, this is Nagendra. I want to also announce that we have started the study group sessions. So whoever want to extend and discuss internally with other team members, right? So they are welcome to join the study group, which will be started tomorrow, Sunday 5 p.m. And the initial 2 sessions they are planning for Docker, and then they will slowly continue with Kubernetes and all. So whoever wants to join, you can send the email to programs@program.com. If you don't have a Teams login, if you have Teams login, I have posted a message there how you can actually request for the joining the study group sessions in the group. So you can follow that, where you can go to study group channel and then you can fill in the form, so that you can be introduced into the study group sessions that will be planned.
Awesome.
I have a question.
Awesome.
Sorry, I have a question.
Yeah, go ahead, please.
I am always hearing this Kubernetes and Knative. What is the difference, or can I use Knative without Kubernetes?
I have never used Knative. I'm not sure.
Okay, and why I should use Knative? Why someone builds Knative as a layer on Kubernetes?
I'm not sure. I have not used Knative. I'm not familiar with it, to be honest. So I'm
maybe
not sure.
you can look it up a little bit and give some basic answers.
Yeah, hopefully.
Yeah. Just want to kind of, before we move on with this question, I just want to follow up on what Nagendra said. For those who do not know what is a study group is, see, this Testopper community is run by the community people like you all, right? So the platform that we provide is the Microsoft Teams. So study group is nothing but, whenever we do some sessions, some of the people who are interested to continue learning on that particular topic, they come together and they start learning together, right? It's always good to learn together with the other people for the motivation than just, reading stuff in the computer all by yourself, right? To kind of get yourself engaged, answer questions. So it's kind of people within the community, they come together and they meet together sometime and they start learning together. It's like, when we are small, what we do, we go to our friends and we do a group studies, right? It's like that, right? The study group is mostly of that concept. And in fact, it is started by the people like you guys who attended the sessions, and many such study groups are ongoing in parallel. In fact, in some of the study groups, people have come together and they prepare for the certifications and they get certifications from Microsoft and so on. So that's what the study group is all about. Looks like there are few people have already come together with Nagendra and the other team and wants to learn. So that's why I believe Nagendra is kind of sharing with you all, hey, if anyone of you also are interested to learn together, please join, right? So that's what it actually means. Moving back to the question of, moreover, right, there was some follow-up question. I believe someone had a follow-up question. Please unmute and ask if you have, please.
Thank you, Ahmed, and thank you, Kader, for this workshop. I have one question, not one, but multiple. So one is with the images. So whenever we deploy, do we store those images locally, or we should always pull from Artifactory?
Yeah, so typically that's a great question, Dilip, actually. Typically the best approach is to set the policy. You can set in your pod template and the deployment, obviously, because deployment has a pod template in it. You can set an image pull policy. You can set a field called image pull policy. You can set it to always. That's typically the best option to do. So you should always make sure that the image will be pulled. However, on the back end, yes, the image will be stored for a short while in that container registry inside the local Docker inside your inside the node where it is. So take an AKS cluster, for example. Obviously, every node, or even if you build your own, you have to have a container runtime in there. That container runtime, when it pulls images, it will cache them locally. It will make them available locally. And then it runs them. So that's how it works. So, but typically in an actual production setup or in a QA or whatever setup that is actually running your applications, I would advise to have an image pull policy of always. So whenever you actually deploy a new image and push it to your Artifactory or your container registry, whatever you're using, once you deploy to your cluster, you update your deployment to a new image tag. And I would even advise to use the hash, the SHA digest of your Docker image, not even the tag name. Once you do that, it will automatically pull that new image, especially if your policy is set to always. So it will always pull a new, fresh image rather than use the local one or anything cached.
Thank you, Ahmed. So we are using that SHA digest, right? So just to make sure that our image is not corrupted, right?
It depends on what use case you would want. It's nothing specific to any company. Everyone is free to how they use it. Even if your CI, your build pipeline, always make sure that your image has a new tag every time you're putting a timestamp or putting always an incremental index in there. You don't really have to use SHA digest, but the SHA digest will make a difference if you use the same image tag multiple times. Then it will not look different for the Kubernetes cluster, but the SHA digest would look different because it will always be unique. So it depends on the policy being followed on the build pipeline.
Okay, thank you. Thank you.
No worries.
All right.
I have
Yeah,
a small question because of the question before it comes up. How do you are doing then the parameterizing? You know, if you have a YAML file, for example, where you want to have, because of the security reasons, the parameterizing in another JSON file.
Yeah, you can use any method you want. There are a lot of tools for deploying to Kubernetes. You can go ahead and build your Helm charts with a very advanced parameterization there, or you can build a simple script that will always replace your variables within that. So you can tokenize whatever you wish, any piece that you want to make it a variable. Obviously, there are things that are advised, like the service name, the tags on it, especially the version tag, for example, the image, the image tag name, the image name, the repo name. So many things should actually be parameters, because you're not going to build a template for each thing. You're going to have a few templates probably that match your types of services being deployed, your ports, number of replicas, things like that can be parameters. And you have a script that you pass variables to, and based on your pipeline, whatever tool you use. If you're using Azure DevOps, there are really easy ways to do that with a simple script that will always replace, before it actually deploys your template, will replace it with the correct variables that are specific to that release pipeline and release what is needed.
So are we going to have a session on Helm?
Not in this track. This is the beginners, because you already heard a few comments that there was a lot of information here, and everyone is still a beginner. Maybe after everyone goes through that study group and they study more on their own, maybe Kader, sometime next year or something, we can have something more advanced.
Yes. I would kindly recommend that if you guys wanted to learn some topics, advanced topics in Kubernetes, please put your interests in the Testoper Codeathon channel in the team, so that would allow us to kind of organize the future sessions around those topics. I know that Tushar, you have raised your hands. Do you have any question, please? Turhal?
I already asked my question. Thanks.
All right. So considering the interest of time, let's close the call. We are 11 minutes past. Just make sure that, like I requested and also Ahmed mentioned, if you have any additional topics to learn, please post it in the Testoper Codeathon channel. We will make a note of it and we will organize the sessions. For this year, we already have lined up the session till December 25th. Next week is going to be the last session from Ahmed. After that session, we have a session on Sunday, which is artificial intelligence using Python, right? How do you build for the basics? If you are want to learn an artificial intelligence, how to build around that using Python programming is the session followed by Ahmed's session. If you are interested, you know where to go and register. It's in the Eventbrite for you to register. Okay, and again, just make sure that you continue spreading our good work to everyone, and that's the only way that we get happiness of what we are trying to do. As well as please do refer to your managers and your company about Testoper, so they can sponsor, which kind of cover some of the tools that we are using, cost and so on, as a non-profit organization, right? So just wanted to let you know that. With that, let's close the call. Ahmed, last word to you, and we can close the call.
Nothing much. Thank you, everyone, for attending. Looking forward for the last session, where we're gonna dive a bit deeper into actual Azure Kubernetes service, and you'll see the power of Azure there and Kubernetes. So, thank you. Looking forward to the next session.
Have a great weekend. It's a long weekend for those who have joined from Canada. Maybe not from other regions. Enjoy your weekend, and talk to you all soon. Bye-bye.
Thank you. Thank you.
Thank you.
Thanks. Bye.
Bye.
Thank you.